Quantum computing is one of the most exciting new technologies on the radar, and you'll know that I've been following the progress closely for years. In the past months, weird things have been happening. And when I say weird, I don't mean quantum weird, where a particle goes through two slits at once. I mean business weird, where a company goes through two roadmaps at once. Let's have a look. But first, what's a quantum computer? Quantum computers perform mathematical operations with logical units that have quantum properties, the so-called quantum bits or qubits for short. I sometimes hear people say this gives quantum computers special power because the number of qubits grows exponentially. If you have a qubit with two states, 0 and 1, then you can combine it with a second qubit to a product state. Then you have 0, 0, 0, 1, 1, 0, and 1, 1. That makes 4. Take a third and you have 8. For n qubits, you have 2 to the n. It indeed grows exponentially. Yes, but actually that's the case already for standard bits. The quantum advantage does not just come from combining the qubits, but from the possibility to entangle them. This means not only do you have 0, 0, 0, 1, 1, 0, and 1, 1, you can also take sums of those with arbitrary prefactors, say 0, 1 plus 1, 0, with weights to tune. Now you see, these states don't exist in a standard computer, so you have many, many more states you can calculate with. And this is basically why quantum computers can perform certain calculations much faster. Alas, this advantage only becomes relevant for a large enough number of qubits, somewhere in the range of some 100,000 to 1 million. One of the diagnostics I like to look at is IBM's roadmap to quantum computing. If you look at their roadmap from a few years ago, they were planning that by 2025 they'd have more than 4,000 qubits, and by 2026 they'd be scaling to 10,000 and up. If you look at their current roadmap, these qubit numbers have just disappeared. Clearly something didn't quite go according to plan. Instead, IBM and others have been quietly shifting goals. First, they claimed that noisy quantum computers could have practical uses already. Unfortunately, these uses were nowhere to be found. Now they use hybrid approaches that combine both conventional and quantum computers. The advantage of those is that you can't tell what the quantum part was good for. IBM has, for example, recently announced they used quantum-centric supercomputing to simulate a big protein complex. Quantum-centric is new speak for hybrid approaches. In this case, most of the calculation was actually done by a classical supercomputer, and they say in the paper themselves that the results of the purely conventional and partly quantum computation are comparable. Don't get me wrong, this is all very interesting and I think it's cool they're doing this and so on, but this is still far off any practical use. When it comes to practical uses, all we have are increasingly bizarre claims like that AI and quantum computing could deliver on the promise of personalized medicine, or that quantum computers could boost AI. When in doubt, sprinkle AI on it. It's like the parsley of business. That doesn't deter the governments of the world from pouring money into it. I already reported recently that China has made quantum computing part of their new 5-year plan. Now, rather predictably, the US government has ramped up their investments into quantum computing as well. Just last week, they put a total of $2 billion into quantum computing, which, I remind you, is the technology that so far has zero practical use. Global Foundries promptly launched Quantum Technology Solutions, a new quantum business for the quantum industry and its pipeline of quantum innovators. IBM says they're building a quantum foundry for quantum wafers to power America's quantum leadership, quantum innovation, and quantum ecosystem. Wow, so much quantum. Who'd not be impressed? What the heck is a quantum wafer, you ask? Yes, good question. IBM and Google and Amazon use superconducting circuits as qubits. One of their main benefits is that you can print them using standard chip production methods on the standard silicon wafers. They are not standard microchips. You need to print the wires with materials that become superconducting at low temperatures, But the production of the chips has never been the main problem. The problem is to use the chips in combination and find a use for them. The one application for large enough quantum computers that no one really doubts is that they could break some old encryption protocols. But this is not exactly a use case for the average person, and once the old protocols have been decrypted, that's that. The other use cases that you often hear, quantum chemistry, material science, logistics and finance, have all eroded one after the other. Either because AI is doing things that quantum computing was supposed to solve, or because no one could actually honestly find something useful to do with them, even theoretically. To me, all these billions being thrown at quantum computing looks batshit crazy given the low expected return on investment. This is particularly obvious if you compare it to nuclear fusion, which has a fraction of the funding but dramatically clearer return on investment. Yes, I'm now defending nuclear fusion as the practical option. This is how weird this has become. Physicists have been arguing about dark matter for almost a century. And now, after all this time, their most favorite evidence for dark matter disappeared. This isn't just an interesting development from a scientific perspective, it's also a good illustration for what's going wrong in this research area. I have a brief summary. Dark matter is supposedly invisible stuff that makes up 80% of the matter in the universe and that makes itself noticeable only through its gravitational pull. But decades of attempts to measure even a single one of the dark matter particles failed. The alternative explanation for the observations is that Einstein's theory of gravity is wrong and must be replaced by a different theory, which is called modified gravity. Astrophysicists have invented dark matter to explain multiple observations that just don't fit to Einstein's theory. Galaxies rotate too fast, galaxy clusters move too fast, gravitational lenses are too strong, structures form too quickly, and so on. But their proudest piece of evidence has been the bullet cluster. The bullet cluster is a collision of two big galaxy clusters about 3.7 billion light years away from us in the constellation Carina. The reason the bullet cluster is so interesting is that we have two different ways to measure it. The one is a measurement of electromagnetic radiation in the X-ray range. From this, one can infer the distribution of hot gas in the clusters. This is shown in red in this image, overlaid over the visible light from the galaxies. The other observation is the distribution of all gravitating mass inferred from gravitational lensing. This is shown in blue in this image. You can clearly see that the total gravitating mass seems to be elsewhere than the hot gas of the cluster. Astrophysicists interpret this to say that these two galaxy clusters passed through each other like this, and there is a component of each cluster's mass that just passed through the other cluster. It's dark and basically collisionless, that's the dark matter. The normal matter, on the other hand, did collide and was slowed down in this process. The bullet cluster is relevant because not only do astrophysicists claim that it's evidence for dark matter, they also claim that it's evidenced against the alternative, modified Newtonian dynamics, MOND for short. This is because in MOND one changes the way that matter creates a gravitational pull. At low accelerations, gravity is then stronger than Einstein said. But in MOND, gravity still pulls in the same direction, namely that created by the normal matter. The bullet cluster seems to say, no, that doesn't work. The news is now that a group of researchers from the University of Bonn say that the observations of the bullet cluster are fully compatible with MOND after all. They claim that the standard explanation of the bullet cluster observations undercounted ordinary but dark matter, such as white dwarfs, neutron stars, and black holes, left behind by an early generation of massive stars. They used the most recent data from the James Webb Space Telescope and compared it with a model in which the galaxies contain more massive stars than previously assumed. They find that with the new data, realistic amounts of ordinary matter suffice to make the observations compatible with MOND. This doesn't rule out dark matter, but it means that the bullet cluster no longer rules out MOND. Or does it? Well, that's where the problems start. The bullet cluster has never been good evidence either for dark matter or against MOND. This is because to fit the observations, the two clusters must have collided at enormously high velocity. Where the clusters would get such high velocity is difficult to explain in a universe with dark matter. It's actually easier to explain with MOND. The other issue is that no one in their right mind expects MOND, a phenomenological model developed to describe time-independent situations, to correctly describe a strongly dynamical situation like this. For this, you need a more complicated modification of gravity, like, for example, John Moffat's TEVAS, and he showed ages ago that this does indeed fit with bullet cluster observations. That said, either way you look at it, the bullet cluster is just one specific instance, and a statistical outlier at this, which is not good evidence one way or another. And this brings me to today's main point, namely the question of why so many astrophysicists nevertheless constantly refer to it as if it tells us anything. The reason is almost certainly that it's a deceptively simple shut-up argument. They began using this in 2008 with the first observations, and initially I saw this mostly for science communication purposes. At this point, I think astrophysicists still realized it's a nice argument, but scientifically not a good one. But then over the years, they began to believe it themselves. Especially younger people no longer question it or even look at the evidence, because anyone who questions the evidence for dark matter is a crank anyway. You see the problem? Now look, you'll know that I'm neither a fan of dark matter nor of MOND. These ideas both have too many shortcomings. But the problem is that even after all these years, these two camps are still basically not talking to each other. Each side has dug themselves into a hole where they insist they are right and the other side is wrong. And that's why we're stuck. And that's why I give this paper an 8 out of 10 on the bullshit meter, because I think pretty much all papers that have been written about the bullet cluster are a waste of time. Subscribe for more grumpy takes on the miserable status of physics. We might finally know what the hum is. That's a strange phenomenon which people around the world have reported for decades, a persistent sound at low frequencies with no obvious source. The authors of a new study now looked at some of the most often proposed explanations. And this is what they found. The hum with a capital H has been reported at least since the 1970s. It made its first entrance into the scientific literature in Bristol, where hundreds of people complained about a low persistent rumble. Since then, similar reports have come from multiple cities in the US and Canada, but also from Germany, Norway, and Australia. Some estimates suggest that roughly 2 to 4% of people report this kind of persistent low-frequency sound, though I'm highly skeptical that this estimate is correct. 2 to 4% is a lot. That's enough people to form a political party, though in this case one with a very monotonous anthem. The hum is often described as resembling a distant diesel engine, a transformer, or a pump. People have come up with dozens of explanations that range from the mundane to the bizarre. Factories, fans, wind turbines, power lines, submarine communications, geological vibrations, resonating electromagnetic fields, underground tunnels, secret military operations and mind control experiments, UFO bases, and of course, aliens. The problem is that not everyone hears the hum. This naturally leads to two possible explanations. Either some people hear sounds which aren't there, or there's really something humming, but not everyone can hear it. It's not just a scientific mystery. The hum can also negatively affect people's lives. Multiple studies have found that low-frequency sound, roughly in the range from 10 to 200 hertz, can cause extreme distress in some sensitive people, anxiety and sleeping problems, and that standard noise measurements can underestimate the low-frequency sector. Low-frequency sound has also been proposed as a possible explanation for why some buildings feel haunted. The authors of a recent study exposed 36 volunteers to music, sometimes with low-frequency sound at about 18 Hz. That's below the range where you can actually hear sounds, and it's called infrasound. The volunteers could not reliably tell whether the sound was on, but when it was on, they had a stronger stress response measured by higher levels of the stress hormone cortisol. They also reported more irritability. The point is not that infrasound makes people see ghosts. It's that low-frequency vibrations from pipes, ventilation, or machinery may make a place feel unpleasant and unsettling, and if people already think the building is haunted, they may interpret that feeling as a presence. So much about ghosts, but what is the hum? Some of the reported hums clearly are real sounds. In Windsor, Canada, for example, residents complained for years about a low rumble. These complaints stopped after a blast furnace operation at a nearby steel plant paused during the pandemic in 2020. A hum reported in West Seattle was traced to a vacuum pump used to unload cargo from ships. After the company replaced the silencers on the pump, reports of the hum stopped. In Sausalito, California, a mysterious hum turned out to be the mating call of certain fish. Okay, but what about all the rest? The authors of the new paper recruited 28 people who reported hearing the hum. The first thing they tested was whether these people have unusually good hearing in the low frequency range when compared with the control group. The answer is no. The hum hearing people were not exceptional. A second hypothesis they tested is whether the hum hearers have a condition in which the inner ear itself creates sounds. It's called spontaneous otoacoustic emissions, though they're usually at a much higher frequency. The researchers looked for that but found nothing, so they ruled this out as well. These results, the authors conclude, suggest that the reason behind hearing low-frequency sounds is often tinnitus, so that's a real perception of sound caused by firing nerves, but not caused by an external source of the sound. So it's not like this paper explains every hum that's ever been heard. We know that some of them are real sounds from the cases that have been resolved, but this study makes it implausible that hum hearers just hear better than others, and more likely that it's similar to tinnitus. I give the paper a 5 out of 10 on the bullshit meter. It's a good study by way of intention, but the sample group is quite small, and the people in the control group were much younger than the hum hearers, so that's not a great control. Also, if it's a real sound, I'd not expect all of the hum hearers to actually have better hearing, because once rumors start, you'll get a sort of social contagion where some people believe to hear things. The brief summary is that if you hear strange sounds at 2 a.m., it's probably the boiler and not aliens. Thanks for watching. See you tomorrow.